I'm going to read some notes to you about transverse waves. Later on down here in this part of the notes, we'll use that to label your second page there. But what we're trying to get done here is that we need to understand that waves have different properties and interactions that affect the world around us. So properties are characteristics. We've talked about physical properties and chemical properties, like is it a solid, a liquid, or a gas? Is it reactive? Is it malleable? Those are properties of substances. In this case, we're going to talk about the properties of how energy moves, okay? And interactions just means that waves can make things move. Waves can make things heat up. Waves cause things to have work done to them. And we'll talk more about that as an important concept about waves, because waves are a form of energy. All right, enduring understandings. It would be perfect if students will apply their understanding of waves as a vibration that carries energy, not matter, over distance to describe their properties, the properties of waves. Apply a knowledge of wave properties to wave interactions, and have an understanding that waves can be used for communication purposes and many, many other things. All right, so some of the wave properties. Letter A, waves. This is disturbance in matter as energy passes through the matter. The energy displaces the matter it travels through. Displaces means to move it out of its current location. This means the matter moves away from the energy up and down, back and forth, but always goes back to its original position after the energy has passed. I like to think of this as if you had a giant pan of Jell-O and you gave it a smack. It would wiggle all around, but it would go back to being exactly the same position as it was before. Because you hit the Jell-O, you added energy, you caused a wave. The up and down movement is what causes the wave action. So think about that Jell-O wiggling around. The vibration of the Jell-O is a wave. There are two types of waves. We have transverse and longitudinal waves. Transverse and longitudinal waves are both energy being moved, but they have different shapes as far as our diagrams go. Transverse waves, these waves are generated as energy moves the matter up and down, which is perpendicular to the direction of the flow for the energy, which is horizontal. So if the energy is going this way, the particles are vibrating up and down. And that's what this diagram represents. So the energy would be traveling, and the particles would be vibrating up and down as the energy goes through. This is the shape that you would see at the beach, perhaps. And this is, of course, a perfect drawing of one of those. The water at the beach doesn't act as perfectly as our drawings. Parts of a transverse wave. And when we get through with this part, we're going to label the other part, the other paper. The crest, this is the position of maximum positive displacement, the highest point. Displacement means the particles that are being vibrated have moved the greatest distance. So this is the position of maximum positive displacement. The crest is at the top of a wave. Okay, so here's one wave, go all the way through. There's the next wave, so crest and crest. So number one would be crest. This is the same word that we would have if we had a bird. The feathers on top of a cardinal's head or a blue jay's head, those are called a crest because it's at the top. The top of a mountain is called a crest. All right, the next word, and you're welcome to pause this video if you need more time to write the word crest on that label. The next word is trough. Now please look at this word, and it's not very clear. T-R-O-U-G-H. Trough. A lot of kids want to say this in many different ways, but this is a trough, the position of maximum negative displacement, or the lowest point. So the troughs on our notes or on our diagram are going to be down here for number 3. So the trough is this lowest part. I learned this word trough when I first read the book Charlotte's Web, because the Wilbur the pig ate out of a trough. They poured his food into a thing that was shaped like this, and it was a trough. So crest, trough, T-R-O-U-G-H. Once again, you are welcome to pause the video to get your labels. Amplitude. The amplitude is the total measurement of displacement from the equilibrium position, a flat line. Some people will make this call this the resting position. So let me point out the resting position, and then I will point out how to figure out the amplitude. Let's get this out of the way. So the resting position, or the position of equilibrium, is going to be number 4. So this is the resting or equilibrium. So this is where the particles that are being pushed up and down by the energy of the wave, where they reach the spot that they're going to return to once the energy's gone. This would be like the surface of the Jell-O. After you smack the Jell-O and it quits wiggling around, it's all going to go back to its equilibrium position or its resting position. So the amplitude, this is the total measurement of displacement from the equilibrium position. So displacement means movement. So the amplitude is number 5 right here. So if we smack our Jell-O and we make a wave go through it, the greatest motion from the resting position to the maximum, or to the crest, is the amplitude. Now, there's another place we can get the amplitude, though. If this changes this much, what about the distance from right here, the equilibrium position, to the trough? Isn't this the same as this? So this is also the amplitude. In our diagrams, the disturbance of the particles of matter, because the energy wave comes through, are going to be equal above the equilibrium or the resting position and below. So the amplitude is this distance. The amplitude is also this distance, because this is equal to this. Matter of fact, I'm going to do this, just like you would do in math class. All right, let's see what else is on our notes. So, but before we do that, okay, so we've got the crest, the trough, which is the lowest part of the displacement. We've got the resting or equilibrium position. Do we have anything else? The wavelength. This is the total length of one complete wave. Now here's the hard part. Here's the part that gets kids. This is just one complete wave. From one crest to another crest, or from one trough to another trough. And so we can measure from here to here. You know what? I need a colorful pencil for this. So there is one wavelength. Okay. From here, from this trough to this trough is also one wavelength. So this distance and this distance are the same. What if we started at this resting position and went through one trough and one crest? So from here to here is the same as from here to here, and the same as from here to here. So the wavelength is the same. What if we go up one spot? That's also one wavelength. So one wavelength, one wavelength, one wavelength, except we've run off of our drawing. But the wavelength in this case is going to be the same. The wavelength doesn't change from one set to the next. So crest, trough, amplitude is from the farthest point away, either the crest and the resting position or the trough and the resting position. The wavelength is the distance from a crest to a crest, or a trough to the next trough, or from any point. What if we went from this part? Excuse me. If we said, hey, we're going to go halfway down the crest to halfway down the crest, that's also one wavelength. All right, let's make sure you get your label done.